As I mentioned in my email yesterday, today is the final exam review session. So pretty much the only information I have about the exam at the moment is that 1/3 of the material on the exam will be from Unit 3, and 2/3 of the material will be from Unit 4. And besides for that, that's all the information I have at the moment. So the exam's created by a course coordinator, so I don't have any other information at the moment. If you haven't done so already, please sign up for the final exam through the document that I posted in my math lab. The deadline of doing so is today, or tonight rather, by 11:59 p.m. There's also that corresponding contract that I wanted you to submit to the shared Google Drive folder. Just printing out or writing out the bullet points there and signing and dating down at the bottom, making sure you understand the conditions of the test. Besides for that, everything else was really everything was summarized in the email sent out yesterday. So please read over that if you're confused at anything throughout, and just be wary of the deadlines as well. I'll move the homework back to tonight and the quiz back to tomorrow. And then there's a few other assignments as well. So make sure you get those done. But hopefully you notice at the very bottom, there is a practice exam for the final exam. So I encourage you all to work on this, as this will be your best way of studying for the final. For this class period, I'm going to go ahead and go through the problems in this exam and just talk about different strategies for doing these problems. So let's go ahead and get started. So yeah, we can go ahead and just go through these one by one. So for a problem like this, it's just knowing how to graph a logarithm and also knowing how to apply transformations. So here they give us the function of natural log of -x. And with natural log of -x, we need to determine all the transformations before we graph this particular problem. Since we are not adding or subtracting any numbers, that tells us that we are not shifting at all, because we are not adding or subtracting any numbers. Instead, we are multiplying a -1 to the x. So multiplying a negative to an x, this tells us that there's going to be some sort of reflection. So this is a reflection about, so when it's a negative on the x, that tells you reflect about the y-axis. So it always alternates in that regard. So that's really the only transformation that's applicable here. We reflect about the y-axis. So that's why I'm going to select that choice over there on the left. Additionally, it goes on to ask us to, well, go ahead and graph the logarithmic function here. So when I open up the graph, I'm going to go ahead and select the logarithmic tool as opposed to the exponential one. So when I click that one, click anywhere on the graph, it brings us this box. It already has the correct base for us. Since we have a natural log, that is a base of e. So the base is already correct. The only thing we have to change is the transformation that we are applying. It's a reflection about the y-axis, so we want to reflect over the y-axis. And so the shape changes to the shape right here. And that is all we have to do for this graph, because that's the only transformation we found. So hopefully so far so good. And from here, so now that we've graphed, we can go ahead and figure out a few aspects of the graph. In particular, they want us to find the equation of the vertical asymptote. So now that we have the graph, the vertical asymptote, remember vertical's up and down. So where is there a barrier up and down for which the graph just abruptly stops at? Or gradually stops at, rather. And it seems like there's a barrier right here on the y-axis in particular. Because you can see that the graph slowly starts to approach that barrier, but never quite crosses it. So really, the vertical asymptote would be at x is equal to 0, because that's the equation of this line right here. That's x is equal to 0. The other indication is that the x-axis, where does that horizontal line cross the x-axis? At 0. So that is the equation of the vertical asymptote. And from here, we can determine the domain because we do have the graph available. So the domain, it's how far to the left versus how far to the right. To the left, we can go infinitely so negative infinity on that side. But to the right, there's that barrier. And where's the barrier happening at? Well, we just determined that is at x is 0. So that instantly answers the question for us that the domain is from 0 to infinity. Or actually, I'm sorry, I just contradicted what I said. Negative infinity to 0, sorry. Negative infinity to 0. And I'm using a 0 with a parenthesis instead of a bracket because 0 has an asymptote. So we don't want to include 0. That's why I'm using 0 with a parenthesis instead of a bracket. And then we can go on to find the range, which the range of any logarithmic function is always all real numbers. But looking at our graph to further validate that, the graph goes up forever and the graph goes down forever. So it's all real numbers. So that would conclude this problem. So does anyone have any questions about this one before we move on? If not, I'll go ahead and proceed to the next problem. All right, so what will a $90,000 house cost 8 years from now if the appreciation averages 6% compounded annually? So hopefully you recognize quickly that this is a compound interest problem. And there was a collection of formulas I gave you for this section. So it sounds like the what we're looking for here, as indicated by future cost, is that we're looking for A. And so that tells us the formula we want to be using is exactly this one. And another reason why I'm choosing this formula is because we are compounding annually. This is a discrete compound as opposed to a continuous compound. So this tells us that we can actually achieve a value for n because we are compounding annually. Because we are compounding annually. And so from here, we can go ahead and find the other values that we need. R, so it's 6%, but we need to write that as a decimal. The time is 8. And the principal, or the original value, is 90,000. And from here, now that we have all of these values, we can go ahead and plug them into our formula. So 90,000, 1 plus 0.06 divided by 1 raised to the quantity 1 times 8 And the good news about this is we can plug everything into the calculator. We don't have to do anything else. If you put all the parentheses correctly, as I have them stated on my screen, then you can plug them into the calculator with that same number of parentheses, and you should get the right answer. Plus 0.06 divided by 1, close parentheses, raised to the open parentheses, 1 times 8. And if you did everything correctly, the answer you should get 143,446.33 after we round to the nearest cent. $143,446.33. So it's a simple compound interest problem. So hopefully this one should be fairly straightforward. Does anyone have any questions about this one before we move on to the next problem? If not, let me go ahead and do exactly that. So I'm not going to do this problem because I did this problem for my previous section, and I'll just go ahead and have both videos up so I can do more problems that way. So I did this one in my other video, which I guess I'll call that one part 1. So I'll skip that one. So let me do a problem like this. So as I mentioned in the beginning, 1/3 of the final exam material will come from the Unit 3 material. And this comes from Unit 3. So let's go ahead and talk about this problem because this very well could possibly show up on your test. 2x to the third is greater than negative 10x squared. So this is one of the polynomial inequality problems. So it comes from that section. So, I mean, if anything were to come from this section, I would expect one good problem from it. So from here, what we need to do, so this is a polynomial inequality, but to set up the polynomial, we need to make sure we have a standard form set up. This is when it would be good to add the 10x squared on both sides to get 2x to the third plus 10x squared is greater than 0. So now it's in standard form. It's all the exponents are in descending order, which is good. And from here, now we can go ahead and try to factor. We want to put this polynomial into a factored form now. And this can be done by noticing what all the terms have in common. So it looks like they all have a 2x squared in common. It looks like this is the common factor, 2x squared. And so if you take 2x squared out of 2x to the third, you're left with x. And if you take 2x squared out of 10x squared, you just get 5. Because it's with the numbers, it's like you're dividing. So 10 divided by 2 is 5. And just to verify this, you can always distribute back in to make sure you did not factor out incorrectly. But now we have the factored form here. And so what we want to do now that we have the form factored is we need to find the zeros, because that's going to tell us how to break up our interval. So each one of these will give us a different 0. Each product, that is. So I'm setting them equal to 0 to find the zeros first, and then we'll deal with the inequality later. So over here, we can divide 2 on both sides to get x squared is equal to 0, and then ultimately x is 0, because when you take the square root of 0 is 0. And then this one on the right-hand side is a little bit easier. So we have two zeros. So we have two zeros, 0 and -5, which means, so hopefully you recall from this section, we normally made a number line and put the zeros in order. Now, what this problem requires from us is that we need to provide the intervals themselves. So the intervals themselves, so this would be one interval. I'll use a different color for this one being another interval. And then this would be yet another interval right here. So those intervals are going to be exactly what I put into the interval row. The first one that I have in blue seems to go from -infinity, and it stops at -5. And then the next interval starts at -5 and ends at 0. And then finally, the final interval starts at 0 and goes all the way to +infinity. So from here, we can determine the sign of each one of these intervals. So notice right here, it wants to know whether the sign is negative or positive. And normally this is when we use a test point. So the test points could be -6. And there was two ways I explained this. You can either use multiplicities or you can use test points. In either case, you do have to find an initial test point. So -6, we need to figure out the sign that it contributes to. So when x is equal to -6 as a test point, we plug that back into the most simplified form. And what we get, well, actually, we can throw all of this in the calculator. 2 times -6 squared, -6 plus 5, we get -72, which is, of course, a negative number. So we found the test point of -6 from the first interval. So that's why I'm going to put negative for the first interval over here. And so, again, I explained this problem in two different ways. You could find more test points if you wanted to. So a test point here would be -1. And then you could find a test point here of +1. But you can also use multiplicities. The multiplicity of -5 is 1. Because that's the exponent of the factor. And the multiplicity of 0 is 2, because that's the exponent of its factor. And using these, this tells you that you're going to cross and touch. So in other words, since this region is negative, then by crossing, we will immediately get a positive value over here. Or if you plug in the test point of -1, you should get a positive number. And with 0, 0 touches, which means you will not alternate the sign, which means you will get a plus over here as well. Or additionally, if you plug in the test point of +1, you will find that you get a positive number. So you're welcome to do it either way. But this is what you ultimately end up getting. And so what this table does, because we're looking for values greater than 0, we're looking for the positive values here. And the positive values that we found, the positive intervals, have highlighted over here on the table. This would be -5 to 0 with a union 0 to infinity. So this is this process for polynomial inequalities. So if anything, I would expect maybe one problem on here, if that, on the final exam, if that. It might ask you to do the table, it might not. Again, I don't know what they don't let me see the final exam. So does anyone have any questions before we move on? If not, then let's go ahead and move on to the next problem. Okay, so there's an amount that's invested at an interest rate of 6.8% per year, compound continuously. And they first want us to find the exponential growth function. So the exponential growth function, that's just a fancy way of saying it's referring to the PERT function. And they want us to type in the, let's see, the exponential function that describes the amount in the account after time t. So they don't want us to plug in t quite yet, but they want us to plug in everything else. So they want you to plug this exponential function in a very particular way. So instead of just writing the exponential growth function as the PERT formula, we don't have to put, we know that P is 13,964. So P is the original amount. And they do say that the original amount is, well, the 13,000. 13,000, oops. 13,964. And they also tell us that at the time, not the time, I'm sorry, the rate. They tell us that the rate is 6.8%, which we need to rewrite as 0.068. So we can go ahead and plug that in for R as well, 0.068. So this would be the exponential growth function. You're plugging in P and R, but not quite T yet. And then they say, what's the balance after 5 years, which means plug in 5 for T. So we can go ahead and do that. So again, this is a compound interest problem. And so 964 e raised to the 0.068 times 5. And luckily for us, this is a calculator problem. 13,964 e raised to the 0.068 times 5. And if you typed in everything correctly, 19618.69. So that would be the balance after 5 years, after the interest is applied, compounded continuously. So does anyone have any questions about this one before I move on to the next problem? Okay, let's go ahead and do so. So this is from Unit 3. It's a simple, it's a simple composition problem. So this mainly makes sure that you know how to construct a composition of functions, given that f of x is the square root of x, g of x is equal to 3x plus 5. And so f of g of x tells you that the outer function is going to be f. So the outer function is going to be f, and what you plug into it is the g function. So the outer function is the square root of x, but you don't put x, you put whatever g is. So really that's, you're plugging g into f, in other words. So that's the square root of 3x plus 5. So you're plugging in g into f in that order. And then they want us to find the domain of this. So it comes down to finding the domain of a square root. And this is whenever you set the radicand, everything underneath the square root, greater than or equal to 0. And you solve for x. And we get that x is greater than or equal to negative 5 over 3. Which we can go ahead and type in. Because all they want is an inequality. So does anyone have any questions about this one? Okay, let's keep going. Okay, so this one's one of those logistic models that we talked about in that last section. So for this one here, first they want us to determine the number of people infected after 8 weeks, which means we're plugging in t is 8 for t ultimately. So this one's going to be a calculator problem. So primarily the only issue here you may experience is actually putting this in the calculator. So something I may recommend or do recommend is doing the denominator separately. So I'm going to put just the denominator in the calculator. E raised to the negative 0.24368 times 8. And so I get 1.284707535. Negative 0.24368 times 8. Okay. And now you can throw everything in your calculator to get, well, we're going to round to the nearest whole number as well. Six, 7, 6. 11,676. And then in part B, they want us to determine, well, what amount of time will it be until 11,003 people get infected? And so this is one of those very gratuitous problems where you have to set the fraction equal to 11,003. And solve for t. So it's one of these problems. If you've done the homework, then you're probably familiar with this process. I've done a few of them in my lecture videos and in the review session, so I'll go ahead and do it here as well. Start off by cross multiplying. 11,003 times 1 plus 2 e to the negative 0.24368 t is equal to 15,000. You can also go ahead and either divide or distribute the 11,003. So I'll go ahead and distribute it. 11,003 plus, I think this 11,003 times 2, that'll be 22,006 to the negative 0.24368 t equal to 15,000. And then something you definitely do not want to do, you do not want to bring these two together. You cannot bring those two together because that breaks order of operations. The 22,000 is stuck with the E via multiplication. So you cannot break order of operations that way. Instead, all you can do is subtract both sides by 11,003. And so what that gives us is 22,006 e to the negative 0.24368 t. That is now equal to whatever 15,000 minus 11,003 is. Which is simply 3,997. So next, what we can do, we need to get the exponential by itself by dividing both sides by 22,006. .24368t is equal to, and you can either put the fraction in your calculator and get a decimal or leave it exact. If you use the decimal form, then you want to use every digit. I would recommend just using every digit your calculator tells you to be safe. 0.181632282. You can also leave it exact as well. I'll just use the decimal here. And now, since the exponential is by itself, we can go ahead and get rid of the base of e by using natural log. And so now this leaves us with negative 0.24368 t is equal to natural log of 0.181632282. And then there's one more step we have to do, which is divide both sides by the negative 0.24368, and then we're done. Zero 0.181632282 divided by negative 0.24368. And all together, what we get pretty much gets 7. It's 7 point, and there's a whole bunch of zeros, and then a 4, 5. So really, we're rounding until the nearest whole number. So it's just 7. So all that work just to get 7. Really 7. So I'd imagine if this problem does show up on the test, it would just be one problem. Okay. Give you a few more seconds to write down everything, and then I'll move on to the next problem. Okay. Let's move on. All right, so for this problem, we can go ahead and write the expression as a sum and or difference of logarithms. So we're not solving for anything here. Instead, what we're doing is we are simplifying via rewriting the expression as from a single logarithm to multiple logarithms. And that's when we're going to be applying the formulas. So the formulas in particular, for logarithms, we had a product, a quotient, and an exponential rule. So here, we are taking the natural log of a quotient. So we're going to be applying the quotient rule, which tells us that we're taking the natural log of the numerator minus the natural log of the denominator. That's what the quotient rule tells us, is that we can split up one logarithm as two logarithms with a subtraction between them. And then from here, you may notice that the natural log and the e actually cancel out, which leaves us with the natural log of x minus 7x. And now from here, there's nothing really more we can do. So from here, we can move on to the next problem. So here, someone's getting a used car for $10,000 in 3 years. This person wants to invest this money now, so that way they will have $10,000 in 3 years. So the question is, how much should this person invest now? And they do tell us that we're compounding continuously, and we're looking for a value now. So you're looking for P. So out of those collection of formulas that I provided, we want to use the formula that is P is equal to A, 1 plus R over N raised to the negative NT. So that's the formula from the notes. You switch A and P and you make the exponent negative. So or I'm sorry, this isn't the right formula. Because we're compounding continuously, we're using this formula. So that was my fault. Because we're compounding continuously. So that makes us use the PERT formula, but we have to modify the PERT formula because we're not solving for the final value, we're solving for the initial value or the principal value. So the future amount, what the person wants to have in 3 years is 10,000, and 3 years tells us the time. And they also tell us that the rate is 3%. So 0.03. And from here, we can just go ahead and plug in all of the given values. Negative 0.03 times the time, which is 3. And once we plug all of this into the calculator, 10,000 e raised to the negative 0.03 times 3. So they should ask for $9,139.31. And over the course of 3 years, that the interest will bring it to 10,000. So hopefully that should be a fairly straightforward problem. Okay, let's move on to the next one. Okay, so we're going to start off by using transformations to graph the function. So the problem that we have, or the function we have, is 4 raised to the x plus 1. And there's really only one transformation that's happening here. There's a plus 1, which tells us, since the plus 1 is happening outside of the x value, it's being applied to the function as a whole, we go up 1. So when we go to graph this, and also this is an exponential function, so I want to make sure I choose the one that says exponential tool. And so this chart up here comes up. Now it has the correct base for us already. It has a base of 4. So we don't have to modify that. All we need to make sure is that we choose the slider that goes up 1. So as you can see, when I change the slider to 1, the graph simply rises up once. That's all we have to do. Just goes up 1. And so now we have the correct graph. And from here, we can determine the domain and the range, among other things. So the domain of this graph is, it goes to the left, as we can see. Remember, so domain is left to right. It goes to the left forever, so that's negative infinity. And it goes to the right, what seems to be, well, there's no vertical asymptote here, so it goes to the right infinitely as well. Or in other words, the domain of an exponential function is all real numbers, and that's always true. Now the range is not all real numbers because there is a horizontal asymptote here. The horizontal asymptote, you could see that there's a horizontal barrier that keeps the graph from continuing. And so this barrier seems to be right here. So where is that happening at? That seems to be happening at 1. So for our range, well, we need to put this in interval notation. So the lowest we can go is 1, exclusive, because we cannot hit the barrier. And the highest we can go, what seems to go up forever. So this tells us that the range will be from 1, where the horizontal asymptote is at, all the way to positive infinity. And so from here, they want us to also determine the equation of the horizontal asymptote. As we just mentioned, it was at 1, but we need to type it as an equation, which means there better be an equal sign somewheres. So this is going to be y is equal to 1. So the horizontal asymptote is here. This is y is equal to 1. Makes sense because it goes through the y-axis at 1. And then finally, they want the y-intercept, which we can figure that out pretty quickly. The y-intercept is right here at 2, because we already know what the graph is. So it's just 2. So that one's pretty quick to determine. So does anyone have any questions about this one? If not, let's go ahead and move on to another problem. Okay, so we have 4 raised to the negative x plus 20 is equal to 8 to the x. And really, there's 2 ways you can do this problem. The easiest way is to notice that both of these numbers, both of these bases, can be written as a common base of 2. Because 4, so 4 here is just 2 squared. And 8 is 2 to the third. So that's the easiest way. You can also use a natural log, which I'm not going to use here. But if you can't observe that these have a common base, you could also write it as natural log of 4 is equal to x natural log of 8, and you can solve it from there. Because the natural logs let you bring the exponents to the front. But I'll go ahead and keep going with the, so you can do that on your own if you want to do it that way, but I'll go ahead and continue from this part here. So here the base is 2 and the exponent is 2, which means we would multiply these exponents together, hence why I have it written as such. And then same over on this side, 3 times x is just 3x. Now, from here, the convenient part is that the bases cancel. That's why this one is the easier method. And here we get 2 times negative x plus 20 is equal to 3x. And we just solve it like a linear equation. Go ahead and distribute to get negative 2x plus 40 is equal to 3x. Oops. So now 40 is equal to 5x, and then x is simply 8. So does anyone have any questions about this one before I move on? If not, let's go ahead and see what else is on here. All right, so from here, let's go ahead and solve the logarithmic equation. 8x plus 1 is equal to 1 plus log of x minus 6. And so from here, they first want us to rewrite the given equation without logarithms, but we need to modify the problem accordingly first. Now I'm scanning over this problem, and generally the first thing I do is I look for, are there any logs with just numbers, no variables, that I could try to simplify? The answer is no. So, all right. Then my next question is, do I have 1 or 2 logarithms? And I have 2 logarithms, so I need to get them together. because I cannot cancel out these logarithms because that 1 is in the way. So I need to get these logarithms right next to each other. So I'm going to move this logarithm over. And so what happens now is get log of 8x plus 1 minus log of x minus 6, and that is equal to 1. And the reason why I wanted to bring the logarithms together is because now we have two logarithms that are subtracting one another, which means we can go ahead and apply the quotient rule, which tells you how you can bring two logarithms together as one if they are subtracting. You apply a quotient. So now we have a single log with the numerator being the first evaluation and the denominator being the second one. And now we just went from two logarithms to one logarithm, which is great because now we can rewrite this as an exponential, which means you would circle the base, you would loop it over and point it to the evaluation here. The only problem, there's no base. So there's not a base here. So when there's no base, the understood base is 10, which now tells us that 10 raised to the first power is equal to 8x plus 1 divided by x minus 6. So that's what this tells us. And now that actually answers the first part. 10 raised to the first power is equal to 8x plus 1 divided by x minus 6. And then from here, we need to solve for x, which ultimately this resorts to a linear equation. You can cross multiply to get 10 times x minus 6 is equal to 8x plus 1. We can distribute the 10 to get 10x minus 60 is equal to 8x plus 1. And we can go ahead and simplify accordingly. So I seem to get is 2x is equal to 61, and thus x is 61 divided by 2. So that's what I get for the solution set. Okay. Let's go ahead and look at the next problem. Okay, so I'm guessing whoever put in this practice problem did not put A or B. So on the test, they will only have you put in the factored form. So we're not going to worry about the expanded form. So even if it says factored form, or if it says do not leave in factored form, you will, it will on the test have you put it in factored form. Or if not, I'll go in and give you the points for keeping it in factored form. So we're going to just type this answer in factored form here. So what they want, So this is from Unit 3. Find a polynomial of degree 3, and they tell us the zeros. So hopefully you recall, they tell us each zero, so -3, which would tell us x plus 3 for one factor, -1 for x plus 1, and then 4 for x minus 4. And then they also tell us f of -2 is -30. And the reason they tell us that is because there's actually an a up front. So there's an a up front that we need to solve for. And the way we solve for it is by using that last bit of information here. So what we're going to do is some scratch work off to the side where we plug in 30 or -30 for y and -2 for each x and solve a. And then we can write the final answer. So this is -30 is equal to a times 1 times -1 times -6. So -30 is equal to what seems to be 6a. And then we can divide to get that a is equal to 5 or -5. So we found a. And so now we can conclude by plugging the a back in what the final function will look like. And I'll leave it in factored form. So we'll go ahead and continue from here. Okay, go ahead and do this one. So they give us two functions here. F of x is, remember, that's absolute value of x. And g of x is 18 divided by x squared plus 9. We'll start off with part A. F of g of 4. What this means, so mainly this is just for you to remember how you organize this information. You're going to plug 4 into g, get an answer, and then plug that answer into f. So really, we start off with 18 divided by 4 squared plus 9. So that's 18 divided by 25. 16 plus 9 is 25. And it doesn't really simplify from there. And so we plug that into f. So whatever that answer is, we're going to plug that into f, which says all we do is take its absolute value. But absolute value, all that does is it changes, it doesn't do anything to positive numbers, and it changes negative numbers to positive numbers, or rather it's positive equivalent. So here it doesn't do anything. If there was a negative, it would just simply get rid of the negative. But we don't have that issue. For part B, they switch up f and g, and then they want us to plug in 2. So the first thing we do is we plug 2 into f. But that tells us we're taking the absolute value of 2, which is simply just 2. And then we plug that answer into g. So now we have 18 divided by 2 squared plus 9, which is 18 divided by 13. And that cannot be simplified any further. part C, they have f of 1, which means you plug 1 into f, which means we're taking the absolute value of 1, which is simply 1. And then we plug that answer into, well, f again, which means we're looking at absolute value of 1, which is, again, 1. So that one works out pretty nicely. In part D, I'll do that over here. So finally, we're plugging in 0 into function g. So really, this is 18 divided by 0 squared plus 9, which is 18 divided by 9, which is 2. Now we plug that 2 into the g function. 18 divided by 2 squared plus 9, 18 divided by 13. So we actually get the same answer as in part B, just by a coincidence. So primarily, this problem makes sure that you know how to apply composition of functions correctly, because there is an order to it. The order is you go from right to left. Does anyone have any questions about this one? All right. Go ahead and move on to the next problem. Okay, so let's go ahead and simply rewrite this. Rewrite this as an equivalent exponential statement. This one's very quick. For the 2, the logarithm's already by itself. This one just wants to make sure you know the definition. And so when you rewrite it, it's 3 raised to the second power is equal to 9. And that's all they want. They don't want you to simplify it or anything. They just want to see that you can apply the formula or the process for which you rewrite a logarithm to an exponential. So that one's pretty straightforward. So I did a problem like this one in my other sections video, which I have posted in my math lab already for your section as well. So we'll go ahead and move on to, and actually I did this one as well. Okay. So here, this one's going to be fairly similar to one we did, one we did a few problems back. So it says that one of the zeros is 2 and that the multiplicity is 1. So if a 0 is 2, then that gives us a factor of x minus 2. And the multiplicity of 1 means an exponent of 1. So we don't have to really put anything. And then they say that we have a 0 of 3, we would put x minus 3, a multiplicity of 2, which means an exponent of 2. And that's really all we have to do for this, because they tell us that we assume that the leading coefficient is 1. This one isn't really very much engaged. So let's go ahead and move on to another. Okay, so I did this one in the other video. Okay, I actually did this one in the other video. I did that one as well. I did not do this one. So let's go ahead and go do this one. So they give us a rational function. So from unit 3, they give us a rational function here. And from this, they want us to determine the vertical asymptote, the horizontal, and possibly even the oblique, which we normally don't have an oblique asymptote in this class. So I'm just going to go ahead and put no oblique asymptotes. Those normally don't show up in this class. So we'll just focus on vertical and horizontal asymptotes. Now, that means you need to remember the criteria for how to find one if you're not given a graph. The vertical asymptote is, well, primarily when you set the denominator equal to 0. Remember, the vertical asymptote and the domain are very much interchangeable. With the domain, you set the denominator not equal to 0. And for the vertical asymptote, you simply switch the inequality to an equality. So for this one, I'm going to set the denominator equal to 0 because I want the asymptote equation. The domain, it would be not equal to 0. And so from here, you can go ahead and use whatever method you would like to use to factor this. I'll just go ahead and write out what I think the factorization is, and we'll test it. So I believe there's a 5 here, minus and a plus 1. So let's see. That is -5. Okay, so I trust that you can factor by now, so I'll go ahead and just write down the factorization here. And each one of these tells us a different 0. (5x plus 1 is 0. 5x is equal to -1, and x is equal to -1 divided by 5. And then over here, x minus 5 is equal to 0, so x is 5. So we found 2 vertical asymptotes. The leftmost one is the smallest one, so -1 divided by 5. And the rightmost asymptote is 5. So from here, so that takes care of the vertical asymptote. And we can go ahead and look at the horizontal asymptote. For the horizontal asymptotes, so for this one, it's comparing the degree of the numerator and the denominator. So for this equation, the numerator has degree 2, because remember, that's the largest exponent. And the denominator, same thing, degree 2. Because again, it's the largest exponent. So what that tells us is that the horizontal asymptote is the ratio of the leading coefficients. So what are the leading coefficients? Highlighted them. It's 2 and 5. So it's that ratio. So it is 2 divided by 5. And so we do have to type that as an equation. Horizontal asymptote is normally y is equal to, and I had 2 over 5. And I will have to change the previous answers as well. Y is equal to 2 over 5. And for those leftmost and rightmost asymptotes, horizontal asymptotes, you do have to put x is equal because they want equations. X is equal and x is equal. So those would be the corresponding asymptotes. And as I mentioned at the bottom, I put down here at the bottom, there's no oblique asymptotes. We never deal with those in this class. So these would be the corresponding asymptotes for this rational function. So does anyone have any questions? So for this one here, this one is a matter of determining various characteristics about, well, we can eliminate a few of these rather quickly by determining what the asymptotes are alone. So the vertical asymptotes, so there's a vertical asymptote here at x is equal to -1. And there's another one at 1, 2, 3, 4. X is equal to 4. And there's a horizontal asymptote at +1. So y is equal to 1. So just using that information alone, we can already eliminate a few of these. Because to have a vertical asymptote of -1 and 4, that means you have to have factors of x plus 1 and x minus 4. These two are good in that regard, but these two are not. Because notice they have the wrong signs. So it's either going to be part B, or answer choice B, or answer choice D. Now there's really a few ways in which we can determine this. There's actually quite a few ways. One of the ways is we can use the multiplicities of the asymptotes. So as we see on the graph, so for example, for this asymptote, for this vertical asymptote right here, the graph goes towards -infinity on that side. Oops. Towards -infinity on that side. And also towards -infinity on this side. What this tells us, since they are both approaching the same direction, this tells us that the multiplicity is, it has to be even. And same thing for this up here. Since these both go to +infinity on both sides, that tells us again, the multiplicity has to be even. So that means for those vertical asymptotes, we need to have even exponents. Only part B has that for the vertical asymptotes. It has the even exponents, as opposed to part D, which does not have even exponents. So really, it is part B. You can also use zeros as well. You can find the zeros. The zeros for part B. The zeros for part B are 1, 7, and plus or minus 1. Actually, no, not even that. It's just 1 and 7. You actually don't get any from, you don't get any zeros from x squared plus 1. And then this one, the zeros are 1, 7, and -1. And you can check all the x-intercepts. So I'll go ahead and, between this section and my other class that I did earlier today, I think that's a good overview of the problems on the practice test. So I'll go ahead and call it here. So if you have any questions, go ahead and email me. But besides for that, have a good day.